know you can squeeze the acids out of an orange peel to pop a balloon. Yeah. One of my 8th graders' minds.
We will. We're gonna do a class exercise, so you may use Mathematica to complete that exercise if you want to, and it might be necessary. But I'm not gonna be doing Mathematica. That was the coolest. Cool. That was amazing. That blew my mind, literally. The Mars landing video. What? Okay, let's do it.
One of the days actually just a video, which is just a combination. That probably blew somebody's mind in like 1842.
That
you can combine pictures together to make like
a video, a moving picture.
Moving
pictures.
You spin them really fast. Look at that.
All right. Well, it's not time for today's APOD, but here's yesterday's APOD. Come on, you can do it. You got this. There we go. This is it. So it's going to play the sound for me. So this is always a pain in the ass.
Table right there.
That's funny.
One on the table here and one
no, I can do this. Sound. I just want the things to come out of that thing, right?
Yeah.
All right, that's not it. That's me. Nobody wants to see that. Okay, so share. Let's do the whole desktop. Yeah. Oh no, I was so close. I know. Okay, here we go. The first video of a touchdown on Mars ever taken. Parachute deploying, looking up and down. So they didn't get the video, obviously, as this is going on. They're just looking at their instruments, but they've timed the audio of them looking at their instruments to correspond with the video. And even that was 14 minutes late. That's right. 7 minutes of terror. This is amazing. So you're looking down from the rover, which is it's still moving 100 meters per second. I mean, it's still, there isn't much of an atmosphere there, right? It's enough to mess things up, but not enough to really slow it down all that much. So if they just land, it's going to destroy things. Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers per second. Radar lock. So they're now actually real-time imaging the surface, looking for boulders and things, and they have some control over where this thing lands to choose a place that is not have boulders on it. About 90 meters per second at an altitude of 4.2 kilometers. We have confirmation that the window vision system has produced a valid solution in part of terrain open navigation. We have priming of the landing engines. They disconnect from the parachute. They zoom off to one side. This is the zoom over. We have completed our terrain open navigation. Track speed is about 30 meters per second, altitude about 300 meters off the surface of Mars. And now you're actually going to see the dust start to come up. And now the thing separates. Sky crane lowers this thing down onto the ground gently. It's amazing. Look at this. Looking up and down on the left. A car. It's a big car. So much dust. I get chills watching that thing. That's amazing. It's kind of emotional. Yeah, so those videos, by the way, are pretty much taken with off-the-shelf GoPros. I mean, literally, they didn't even build any special cameras. They just hooked these things up and wired them in so that they could turn them on and off at the right times. And it's literally a GoPro on Mars. Exactly. All right, go away now. Go away, go away. There we go. All right, so that's yesterday's astronomy picture of the day. Today's astronomy picture of the day, obviously you can't top that, but it's still pretty cool. Okay, you could, but they didn't. It's a very cool Hubble Space Telescope picture of a rather photogenic galaxy, M66. And I guess, see, amateur astronomers know this stuff. And people, when I say amateur astronomers, think I'm being derogatory. I am not. I kind of wish I were an amateur astronomer, but I know nothing really about, not nothing. I know very much less than many amateur astronomers about cool stuff to look at in the sky. Anyway, this is apparently a part of the Leo galaxy triplet, which I guess is 3 pretty bright and cool to look at galaxies that are all within half a degree of each other. So within a small telescope's field of view. So this is a spiral galaxy. Obviously, it's got a nice prominent bar through the middle, which is, caused sometimes by dynamical forces within the galaxy itself. But also some cool things that we've been talking about in class. These dark clouds are much denser and cooler than their surroundings. And we call them molecular clouds because it's often so cool that hydrogen molecules can form, and you get H2 molecules. These pink regions are often called H2 regions. H2 meaning H with a Roman numeral 2 because there's lots of ionized hydrogen there, because there's lots of bright stars around that are emitting ionizing radiation. Those electrons are getting ionized, those atoms are getting ionized, and it glows pink. Why? Because as those electrons are captured again, you emit lots of photons at the wavelengths as these electrons cascade back down, including sometimes the Balmer line, 3 to 2. And that's a very prominent, the brightest of the Balmer lines, and that's why these things appear pink, because there's lots of Balmer emission from H2 regions. It's not that, obviously, H2 doesn't come from ionized hydrogen, but you have to have energetic stuff around that there is ionized hydrogen around to see H alpha in emission. And that's what you're seeing there. And these guys down here, there's no more gas there. So these are star forming regions, right? This is where you form stars. It gets really bright and hot, and then those hot stars heat up the gas from which they formed and make it glow in these colors. These are regions where the gas is gone, and now we've just got bright stars that are very blue and hot, and all the gas has been blown away and evaporated or sent packing. So lots of cool stuff, even stuff that we're kind of talking about right now in this astronomy picture of the day. Okay, so where were we? We had written down one important equation. I'll write it down again because it's so important. We might need to refer to it again. And that was the Boltzmann equation. And this is NB over NA equals GB over GA times e to the negative EB minus EA over KT. And this relates, again,
electrons in any atom, how many electrons we expect to be at one energy level as opposed to another energy level, that ratio. So this gets us, if you remember, an equation for the n equals 1 and n equals 2 states in hydrogen. An equation looks like this. We solved this on Mathematica yesterday. And from 5,000 to 25,000, this never gets above 5%. They're still almost 90, 95%, 95 to 100% in the ground state at these temperatures. And obviously, the higher temperature you go, the more are at the first excited state. And we had to go to 85,000 Kelvin, if you remember, to get this to 1, where there's equal numbers in the ground state and the first excited state. Kelvin. What?
Do we know of anybody?
That's an interesting question. What's the hottest star we know of? Yes, white dwarfs are that hot. And so, but there may be some regular stars that are that hot too. The most massive stars in the galaxy are on the order of 100 solar masses these days. But I don't know what the temperatures of those stars are. It's an interesting question. What is the hottest normal star that exists these days? It's a good question. Okay, but now, and so this explains, if you remember, why it is that A stars that are much hotter have stronger Balmer lines than G stars, which are much cooler. A stars have about 10,000 Kelvin. G stars are down in the 5,000 to 6,000 Kelvin range. These stars are hotter. We expect more hydrogen atoms to be in the n equals 2 state. And these lines have to be formed by an atom that starts with the electron in the n equals 2 state. If all the electrons in the ground state, you won't get any of these lines. And sure enough, these lines are almost non-existent in the very cool stars. But it doesn't explain why these more hotter stars have weaker hydrogen lines. And we need another equation to understand that. And that's the Saha equation. Saha. So, again, I'm not going to derive any of these equations. It would take me a class to do it, and I don't think you get much out of it. So you can look it up. These come from, atomic physics, nuclear physics, and thermodynamics arguments. So here's the Saha equation. It's not any more pretty. In fact, it's uglier. But it's very useful. So it's again a ratio, not of electronic states, but ionization states. This is a ratio of an ionization state and the ionization state immediately below it. So this could be the first and the 0th ionization state, or the second and the third, or the second and the first, or the third and the second. Ionization state, Ni plus 1, the next ionization state. One more electron ionized. And so there is a 2. We have a Z, capital Z of I plus 1, divided by Ne Z of I. We've got, this is a capital Z too, let me make sure that's big. We've got 2 pi mass of an electron, kT, divided by h squared, all to the 3/2 power. So this is ugly, but these are just linear numbers at least, with modulo of e to the 3/2 power. And then you've got your exponential, e to the negative, I'm going to call this a chi I over kT. So let's define some of these terms. This thing is an ionization energy. From I to I plus 1. In other words, from the ground state of this, how much energy does it take to ionize the lowest bound electron? So, for example, for hydrogen, this would be 13.6 eV. because that's how much energy it takes to liberate an electron from the ground state of hydrogen to an unbound state. Ne, this thing, so H is Planck's constant, K is Boltzmann constant, T is the temperature, 2 pi. We know what KT is. Really, this is the mass of an electron. We need to figure out these Z's, and we need to figure out this Ne. Ne is the number density of free electrons. Why does this matter? The easier what reaction is? Yep. Right. You're on the right track. It's not really an energy argument though. It's simply a, if you have, let's say you had an ionized hydrogen atom, if there are no electrons around, that there's nothing that hydrogen atom can do to become unionized. You cannot go back to this state. The more electrons you have floating around, the easier it is to go from this state to this state. If that number is 0, everything is going to be, once you ionize something, you're done. If that electron goes away, you can't get back down to this state. So it's really just, the more of them you have, the easier it is to get back to this state, which is why this is in the denominator. That's really all it is. So the Z's, what are those Z's? Anybody taking thermodynamics know what those Z's are? You probably haven't gotten there yet for stat thermo. It's a partition function. This is the weighted sum of the degenerate quantum states of the atom. I'm not going to bother to explain that. You can take stat thermo and you probably spend a whole week or 2 weeks or 3 weeks talking about partition functions. They're kind of cool. All you really need to know is how to calculate them. So Z of some ionization state is the sum of J equals 1 to infinity of G's. These are the statistical weights of that particular energy level. Remember, this is a true of a particular ionization state. Hydrogen 1, helium 1, helium 2. This is a statistical weight showing the number of the quantum states at each electron energy level for that particular state. And then you've got an E to the negative EJ minus E. Oh, this is a J. And this is an I. So this is G is a number of degenerate states in J. That's right. Yep. Okay, this is good. This gives us a number density of electrons, but this isn't something we usually know about our stars. We can't usually say the number density of electrons is, 500 million per square centimeter or whatever it's going to be. But because we can't get this number, so but we can there are other parameters of the star that we can use to get a handle on what this number is. Things like the temperature and the pressure and the things that are measurable in the atmosphere of that star. So we know NE want a better quantity. And by better, I mean easier to measure. Equation that relates pressure and temperature, etc. So you know of an equation of state, the electron pressure in a gas. Gases are pretty good ideal black bodies, ideal gases. And so we can use the ideal gas law to get a handle on what this number is going to be. NE times KT. This is just the ideal gas law. So we can rewrite this in terms of things that are easier to measure, like the temperature, and things that are easier to quantify, like the temperature. Electron pressure is a little bit weird. This is just the pressure due to the electrons. This isn't actually necessarily the pressure, the total pressure of the gas, but you can get a handle on what this number is if you do know the total pressure of the gas. So this is the ideal gas law. So you plug this into here, and you get usually the psi equation as astronomers would write it with temperature and pressure instead of number density. And that equation looks like this. No, we don't usually like volume terms either because, well, right. So there is a volume in here really, right? This is capital N over V. But again, we don't really think about, we're talking about the temperature is varying across the star, the pressure is varying across the star. We're usually talking about a local quantity. And so we're more interested in density measurements, which can be defined locally rather than taking the entire volume of some region. That's right. So I'm gonna solve this for NE and use PE and KT here instead of NE. I'm getting rid of NE and replacing it with some things that are easier for us to handle. 2 Zi plus 1 KT over PE Zi 2 pi MEKT over H squared, all of the 3/2, e to the minus chi I over KT. That's the Saha equation. So again, that's just replacing the ZE with KT over PE over here. So you say you want to build yourself a stellar model where you are calculating what this spectrum is going to look like for a given star with a given temperature and a given pressure. What do you need? You need a Saha equation for every relevant ionization state. And you need a Boltzmann equation for every relevant energy level of every relevant ionization state. And it gets worse than that, because if your gas isn't just hydrogen, you need to repeat this for every single element that's in your gas. these get very complex and very, you need computers to solve these equations. It's 90% hydrogen by number. That's right. But, you know, most of these lines, all of these lines are due to non-hydrogen atoms. So if you want to understand the full spectrum, you need to do this for every single, and hydrogen is simple because there's only 2 ionization states, and one of those ionization states has 0 energy levels. But when you get to iron, which has got 26 ionization states, and who knows how many relevant electron energy levels, it gets really complicated really fast. So before you want to go off and be a stellar modelist, just understand that it gets complicated fast. All right, I'm going to leave that up there because that's right. That's right. That's right.
So would we find elements as heavy as iron near the surface?
Oh yeah. Oh yeah. You look at this. You look at these. You'll see every element that is on the Earth in the stellar spectrum. They're all there. So yeah, you'd think that the heavy elements would sink to the bottom, but convection. There's two things at play. Diffusion can actually work in both directions because heavy elements sink, but it turns out there's a net outward flow of photons, and those photons, the bigger elements, tend to be larger, and there's actually a pressure from photons pushing the larger elements outwards, and so there's actually competing downward and upwards effects for each of these elements. In diffusion, it's very complicated. Sometimes the heavy elements get pushed up, and sometimes they get pushed down, depending on the local situation. And the other thing is, those time scales for that to happen are fairly long. And if there's anything else going on, like convection, it just doesn't matter anymore. It isn't even, it's a second, third, fourth order effect. Makes almost no difference. It's a good point. So I'm not going to bother to do this in Mathematica, but if you were, and you were to plot the Saha equation for the first ionization state of hydrogen, the only ionization state of hydrogen, H2 to H1, this is what that thing looks like. So this is not quite this. This isn't N1, Ni plus. This isn't NH2 over N1. This is more typical, N2 over N total. But this is a more easy way to think about what's going on, because this one would go from 0 to infinity as that switches on. This goes from 0 to 1, and you can kind of see where it turns around a little bit easier. But this is pretty easy to calculate once you know what this is. So you can see, where does this turn around? It's all in the non-ionized state, roughly below 5,000 Kelvin. But as you approach 10,000 Kelvin, what happens? All of these things become ionized. And by the time you reach 12,000 Kelvin, almost every single hydrogen atom is ionized. Even though it takes 80,000 Kelvin to get equipartition between the first and second energy levels, it doesn't really even matter because they're all ionized after 12,000 Kelvin. So now we can understand what the Balmer line, why the Balmer lines do what they do. Let's go back. Oh, so this is the whole thing, right? This is for a Balmer line. This is combining the Saha and Boltzmann equation. The Saha equation for n equals 2 to n equals 1, which is giving you a ramp up at this point for the Balmer lines, because the more that are in n equals 2, the more Balmer lines are going to get important. And then this ramp down, because more and more of those atoms are ionized as you go hotter and hotter and hotter. So this is the number of atoms in the n equals 2 state of hydrogen relative to the total number of hydrogen atoms times 10 to the negative 6, right? So this is 1 in a million. This is 9 in a million. And you never get above 9 in a million in the right position in the hydrogen to be able to generate a Balmer line. And this is why the Balmer lines, where do they peak? At 10,000 Kelvin. And that's why. Let's go back to these. Now we can understand this. Again, it's not that most hydrogen atoms are in the right spot to give you a Balmer line. It's still 1 in 100,000, but that's still better than you're doing over here, and it's better than you're doing up here. And that's why the Balmer lines peak in the 10,000 Kelvin range. Combination of Boltzmann and Saha. No, above 10,000 Kelvin, you've got a plasma of hydrogen atoms. Most of them are ionized.
At that point, when there are very few interactions between the electrons and the respective atoms at all, in what ways are we still able to detect, are we looking for the ions?
You're talking about the H2 regions where we're seeing the glow of H alpha lines?
Right. In my conception of it, like we would worry about how whether high ionization of the atoms in the cloud because they're part of interaction between the electrons and without a particular.
No, that's certainly not true. I mean, there's still, so when you get above 10,000 Kelvin, it's true that there aren't, almost all of the hydrogen atoms are ionized, right? I mean, the other thing is there's a pressure term here, right? And so it's different on the surface of a star than it is in the interstellar medium because this pressure term is, so this probably doesn't work for the atoms in an interstellar medium. This is sort of a stellar atmosphere on the surface of a star pressures. So this doesn't necessarily apply, but something similar will. But even though let's say 99% of all atoms are ionized, that's still a continuum, right? There's still electrons being lost and electrons being gained, and there's always any given atom can and will be capturing and getting electrons liberated, capturing electrons and having those electrons liberated, right? And if you've got a molecular cloud that's a parsec in diameter, like a H2 region that's a parsec in diameter, even at interstellar densities, that's, zillions of particles. That's not even a number. It's a very big number. And so even if only 1% of them are glowing at any given time, it's going to be bright. It's going to be glowing in this region. Does that answer the question? Okay. Okay, what time we got? It is 2 o'clock. I've got 20 minutes left in class. I want to do a class exercise. This is a class exercise that is done in the book, exercise 8.15, but I think it's useful. Oh, I didn't want to do that one. This is the Boltzmann and B over NA. And that is answer the question of why. You look at the solar spectrum. The sun's a G star. This is similar to the sun. The hydrogen lines are there. They're kind of strong, but they're not really, really strong. And there's some calcium lines in here that are even stronger. Let's try to understand why that is. So let's work through this example. Which is stronger, H alpha or the H and K lines of calcium? And these are the H and K lines of calcium are singly ionized calcium ground state lines. Okay, so H alpha or H and K lines, which is the calcium 2 ground state. For reference, hydrogen is about 500,000 times more abundant than calcium. For every calcium atom in the sun, there are half a million hydrogen atoms. Okay, so we're going to need 3 calculations to be able to handle this. And I've got 4 rows plus a couple over here. So I will assign each of these to a row. You can't really work together, but you can at least work on it separately and then shout out answers to each other to make sure that you agree. So I need row 1 for hydrogen to calculate N2 over N1 for hydrogen. Oops. This is an ionization state. This is going to be a Saha equation. I need row 2 for hydrogen to give me the ground, the first excited to the ground state in hydrogen to figure out how many are in the n equals 2 level for Balmer. So this is going to be Saha equation. This is going to be Boltzmann equation. Row 3 for calcium, we're going to need to know how many are in the first excited, how many are in calcium 2 as opposed to neutral calcium and doubly ionized calcium. We have to make sure that they're not too ionized. So we need 2 things here. We need N2 over N1 for calcium. Row 4, back row for calcium, we need N3 to N2 for calcium. And these guys on the right, potential spam. I think I'll pass. For calcium, we're going to need to know for calcium 2, how many are in the first excited state versus the ground state for calcium 2. Let's put up some, I'll leave that equation there, some data, some givens. Our temperature in the sun is 5777 Kelvin. The electron pressure is about 1.5 newtons per square meter. We need some Z's. Z for hydrogen 1 is about 2. And Z for hydrogen 2 is about 1. G1 of hydrogen is 2. G2 of hydrogen is 8. Z of calcium 1 is 1.32. Z of calcium, this is 1. Calcium 2 is 2.3. And Z of calcium 3 is 1. G1 of calcium is 2. G2 of calcium 2 is 4. We're not done yet. Ionization energies for hydrogen, 13.6 eV. Ionization energy for calcium 2 is 6.11 eV. Ionization energy for calcium 3 is 11.9 eV. So this is the amount of energy it takes to liberate a ground state calcium 1 to be ionized. This is how much energy it takes the ground state calcium 2 atom to be ionized to be calcium 3. These are going to be important. We're over there. Other things you need, E2 minus E1 of hydrogen is 10.2 EV. E2 minus E1 of calcium 2 is 3.12 EV. Mass of an electron is 9.1 times 10 to the negative 31 kilograms. K is 1.38 times 10 to the negative 23 joules per Kelvin, but even better is 8.6 times 10 to the negative 5 EV per Kelvin. This is going to be more useful to you because it's going to make your EVs cancel out. And finally, H is 6.626 times 10 to the negative 34 joules per Kelvin. And I think for H, that's going to be important because you've got kilograms and other actual random units. You might need both of these Ks. You should use the EVK here because you've got this in EV, but all this stuff is going to be an SI unit, so you probably want the joules for this K. Okay, so see if you can do that calculation for the one that you've been assigned. You got a number? Oh. What? Euro 2. Yeah, you don't need a Chi, Dante. You're just doing this one.
You gave me something else. I got a number.
Yeah, if you're over here, you just want K in EV, and that's the Saha people are actually having a lot better off than the Boltzmann people. Sorry about that. you asked me, or you compare it with them? No, I think the Saha people have it easy. The Boltzmann people have it. Yeah, I do. Yeah, right.
Again, numbers in this class.
Right. It's just a number.
Yeah.
What'd you get?
4.85.
It's pretty close to what I got, but not exactly. Oh, okay. Okay, cool.
I mean, I just took those numbers.
Okay. Well, we've got two people who agree now. Let's write it down. 4.8, you said? Yeah. Times 10 to the minus 9. Great. Any other numbers that we feel confident about? Yeah, Morgan. You like that, Bailey? You got nothing. That's actually what I got. 3.8 or so times 10 to the negative 3. Yeah. Like it? This says that for there's more. No, compared to hydrogen. That's exactly right. That's right. One in a billion, and this is 1 in 1,000 or so. That's right. It's 6 orders of magnitude. It is this 10.2 versus 3.1. It's just way easier to get a calcium into the second energy level. That's right. Have we haven't agreed on a number here yet? 3 very different numbers. All right. What's your order of magnitude? What's your order of magnitude? Okay, I like these better. What are your numbers? Yours 3 times 10 negative 4. What'd you get, Sarah? I don't know why, but yeah, it's definitely about a little more than 7, 10 to the negative 5. It's a whole lot of numbers. The struggle is real. Alex, you got something?
It just looks like all over again. I understand about the same amount.
The physics is interesting for those equations, but they're it's the implications that I want to get to, which is why we're sort of doing an exercise so we can see what these numbers actually do and why they are what they are. Row 3 or 4, you got anything for me yet? What are your numbers? I can settle a disagreement. That's a big number. That's an even smaller number. I don't like either one of them. All right. I've only got about 4 minutes left, and I want to finish this exercise with a punchline. So you straighten it out?
Yes.
Hey, that's nice. Yeah, what you got, Liam? All right, I'm gonna go with 918. How about that? It was you missed it by that much. I love to do this to my astronomy kids. You've probably never been more wrong in your entire life than 20 orders of magnitude. Row 4, have you come to any conclusions yet? Connor, nothing? Just do it. I've already heard their crazy numbers. Nope. How about 2 times 10 to the negative 3? Yeah. Again, just a little bit off. I did the calculation, but the book does this too, and they get the numbers that I get. So don't blame me. Blame actual science and numbers. Okay. So what are the question we're asking? Which has more hydrogen? Which has more atoms available in the states to make those lines? Hydrogen or calcium? So we need to do some. These numbers don't give us that directly. We need to do a little bit more work. How does that work? Well, we really want for calcium the number in N1 for calcium 2 to the total number of atoms in all calcium states, right? We want to know how many are in the ground state for calcium 2 compared to every single other possible energy and ionization state. We're going to stop because we know that pretty much they're all in the first or second ionization state or 0th, and we don't have to worry about any other electron levels really. But if we want to do this right, N tote would have to be a whole bunch more. So what is this? This is the number in the N equals 1 state of calcium 2 divided by the total number N1 and N2 times the number in calcium 2 divided by the total number in 1 and the total number in 2 and the total number in 3. That's really, this is what we want. And we don't have this either directly. We have ratios of things, but we can turn those we can turn this into ratios of things just by dividing through by things if we want to. For instance, let's divide this thing by N1, right? What do we get? We get 1 divided by N1, just 1 plus N2 over N1. And 1, this number we have, right? So we can turn a single ratio into something that is useful for calculating what we actually want to know just by doing an exercise like this. And over here, we can do the same thing. Again, we're interested in N2, so we can divide everything by N2 if we want to. This becomes 1 over N1 over N2 plus 1 plus N3 over N2. We have this one directly. We calculated that one. We don't have this one directly, but we did calculate the inverse of this. So we can just take 1 over the number that we did calculate and plug it into this number. And this will give us, plugging all these, we have this, we have the inverse of this, we have this. That will give us the total number that are in the ground state of calcium 2 to the total number in all other states that we've considered combined. Right? Plug these numbers in. 1 over, I'm not even going to bother. N2 over N1 is a really small number. This is basically 1 over 1. These two are going to be really small numbers. This is also 1 over 1. This is, you get a number that's about 0.995. Virtually every single calcium atom is in exactly the right place to give us those H and K lines, which are ground state calcium lines. Do the same thing for hydrogen. In hydrogen, though, we want the total number in the N equals 2 state for hydrogen, because that's going to give us a Balmer line, divided by N tote for hydrogen 1 of hydrogen 1. Again, similar things. This is N2 over N1 plus N2 times N1 over N1 plus N2 ionization states. We can do the same trick we did up there. In this case, it doesn't matter how you do it. You can divide by N1. This is N2 over N1 divided by 1 plus N2 over N1. This is 1 over 1 plus N2 over N1 for hydrogen. Anyway, you multiply those numbers out and you get a number that is 5 times 10 to the negative 9. So only what for every one hydrogen atom, only 5 times 10 to the negative 9 of them are in the right place, meaning the unionized second energy level, N equals 2 energy level, to create a Balmer line. So even though calcium is 500 times less abundant in the sun than hydrogen is, the H and K lines are actually a lot stronger than the Balmer lines because almost none of the hydrogen atoms are in the right state to give you that line. Okay, I'll stop there. You're salty back there in row 3, and I like it. Did you get it, Connor? Yep. Yep. Homework, yeah. So, I mean, once you set up equations and you can just plug numbers in Mathematica, it's not that hard. And if I ask you to do something like this on a Mathematica sheet, I will probably set up the equations for you ahead of time and just ask you to use them or something like that. No. If I ask you to do something like this on a test, it would let you use Mathematica. Hey, Dante. Oh, by the way, I got an email from Natural History Museum asking for a letter for you. Yeah, and I submitted it, so that's a good sign. Yeah.
Yeah, right. I think like, why not? Yeah.
And the response I got was, thanks, this is very helpful. So hopefully that's in a good way. So I don't know. Yeah, so you're in the running. You too.